Hello, this is lecture number 4 for Nanofabrication Technology course. And as a review, we talk about nanotechnology and synthesis of nanoparticles in general in lecture 1. In lecture 2, we talk about surface energy and how nanoparticles or nanostructure materials change itself according to the minimization of surface energy. In lecture 3, we talk about how to prevent accumulation by stabilization. And there are two ways: electrostatic stabilization and steric stabilization. Now it is time to talk in detail about how to synthesize nanoparticles. And this is what we are going to cover in this lecture. For nanoparticle synthesis, as we mentioned from the very beginning, there are two approaches: top-down, just like milling, that we start from bulk material and try to make it smaller. Okay, we can do milling like for weeks so that the powder that we obtain contains nanoparticles. We can also do thermocycle, just like when you put a glass into a heater and you quench it quickly, the glass is usually break or being broken. If you repeat the process, the glass can keep breaking up, making it smaller and smaller. This kind of thing is called thermocycle. However, both techniques usually give us particles with very broad size distribution, which is not what we want. And sometimes the shape cannot be controlled, so the technique is not quite popular. On the other hand, if we start from bottom-up approaches, so that we start with atoms and let atoms form itself into particles, the trick is how to stop at the nano size. That's what we are going to discuss in this lecture. There are two categories for bottom-up approaches. The first one is called Thermodynamics Equilibrium Approaches. In this case, it starts by using chemicals and precipitate chemicals out, and somehow use nature or precipitation to confine or to makes the particles to be small. On the other hand, the second technique is called kinetic approaches. In kinetic approaches, we normally confine the space of the growth to be small so that the result would be small particles. Okay? In this lecture, we will focus on the first technique or thermodynamics equilibrium approach first. In this approach, it is consisted of 3 steps. First is called generation of supersaturation, nucleation, and growth. Okay, all of these 3 steps takes place consecutively or sometimes at the same time, right? And we will try to control all of these steps. For the kinetic approaches, as I said, even though we will not discuss the detail in this lecture, but in general, I just want to give you a broad picture so that you can compare. For the kinetic approaches, basically there are 2 ways to do the kinetic approaches. First one is to limit amount of the precursor so that the precursor runs out before the particles can grow larger than what we want. The other technique is to confine the space of the particle growth to be very small. And the analogy of this confinement is basically if you have a beaker of 1 milliliter in volume and you put the precursor inside the beaker to do the precipitation, the biggest size of the particles that we can get would equal to the size of the beaker itself, right? So if somehow we can confine the space of the beaker to be like nanometers. If you somehow can create a beaker in nanometer size, then the particles that we obtain inside the beaker will be that small. That's the concept of kinetic approaches. In this lecture, as we said, we will discuss the first approach, or thermodynamics approach. And there are 3 steps. In order to understand thermodynamics approach, you need to understand homogeneous nucleation first. Alright? Suppose we have solution. Let's say sugar and water. Sugar is solute, water is solvent. If we keep adding sugar and water, we increase concentration of sugar in water, or the concentration of the solute increases as we adding the sugar or adding the solute into the solvent. So the concentration becomes higher. If we keep adding up the solute into the solution, at some certain point, we can no longer add more solute. At that point, the solution is called saturated solution. At that point, the solubility or the concentration of the solution, concentration of the solute in the solution would equal to solubility of the solute itself. Okay? And saturation is the thermodynamic state. That's why we call it thermodynamics approach. Okay? Now, the solubility is a function of temperature. If you increase the temperature, solubility is usually increased. Of course, if you cool down the temperature, solubility will be decreased. So imagine you have saturated solution of sugar and water. The concentration of sugar in the solution already reaches the equilibrium solubility, okay, at some certain temperature, let's say room temperature. If you cool down the solution to 5 degrees Celsius, put the solution in the refrigerator, when you cool it down, solubility will be decreased, right? But the concentration of sugar in water already exceed that solubility. So therefore, excess amount of sugar should precipitate out as a solid. That case, you usually get crystals or solid precipitation. Alright? This is conventional process. You cool it down, basically you reduce the solubility, and the concentration that already exceeds that solubility has no choice but precipitate it out. Okay? Keeping the concentration inside the solution to be at solubility at all time. Okay? However, if somehow you can cool it down slowly, slow enough, or if you control how to cool it down for a brief moment before nucleation or before precipitation would take place, there will be a chance that although solubility is already decreased because of the decrease in temperature, but the precipitation has not yet occurred. Okay? If the precipitation has not yet occurred, in that particular moment, just in very brief window of time, the concentration in the solution should exceed solubility. In that case, we call the solution to be supersaturated. Alright? In this supersaturation status is not considered as equilibrium. It's not stable. It's not even stable. If you leave that supersaturation status for a while, precipitation would take place. Once precipitation takes place, the excess amount of solute would change into solid, reducing concentration in the solution, so that the solution concentration remains the same as solubility at all time. Okay? So supersaturation usually is followed by precipitation. But for the brief moment in time, we may achieve supersaturation. The key is how to keep supersaturation that we want. Alright? So, the first step of the nucleation, or the first step of the fabrication of nanoparticles, is to create supersaturation. So you have to understand what is supersaturation. So in summary, supersaturation is a state where the concentration of the solute in the solution exceeds its solubility. This state is not stable. It can be held as supersaturation only for the brief period of time. Alright? In order to achieve supersaturation, we can do several things, mainly two things. First, just like what I gave as an example, we can reduce temperature of the saturated solution. Okay? Just like this diagram, if I prepare a solution by adding sugar and water continuously, concentration of the sugar and water in the liquid should follow the blue line, this line. And solubility, which is a function of temperature, is a property of the solute itself, remains at some certain value. If you continuously add the sugar and water, solution concentration should exceed to some certain value. Okay? It is very difficult to add the solute until solution concentration exceeds solubility. That's almost never occur. Alright? But we can get supersaturation so that we cannot get supersaturation by simply adding up the solution, adding up the solute into the solution. That's almost impossible. The way to achieve supersaturation is to get the saturated solution or the solution concentration really high near the solubility, and then decrease the solubility by decrease the temperature. When you decrease the temperature, solubility decreases, and for the brief moment before precipitation takes place, that particular moment, this gap is called supersaturation, because the current concentration in the solution exceeds solubility. Of course, when you leave the solution for a while, then precipitation takes place, reducing the concentration in the solution to be equal to solubility, and the solution becomes what we call saturated solution. Okay? But this technique is, even though it's easy to understand, is simple in concept, it is very difficult to control, to make it happen just what we want. Because when we try to adjust temperature of the solution cannot be adjusted as quickly as we want. Let's say we have a solution at 100 degrees Celsius and we want to cool down to 80 degrees Celsius within seconds. That's nearly impossible. That's very hard. Alright? So this technique is not quite popular, or is not conventional at all. It's very hard to achieve. On the other hand, the second technique is more popular, is more practical. The second technique relies on the conversion of one chemical species to another. Okay? If we can convert a species that is highly soluble into the species that is less soluble, then we can control formation of supersaturation. Just like this diagram. Suppose I have reactant. I add the reactant to the solvent. I create the solution. Okay? The solution have the concentration higher and higher as I add it adding the solution solute to the solution until it reaches the solubility of the reactant itself. Okay? Now, if I start the reaction, somehow convert the reactant to product. Let's say I have 1 molar of reactant A into the solution. I initiate the reaction to convert A into B. The concentration of the product should be in the rough approximation or almost the same level as the concentration of the reactant itself. Okay, the concentration may not be the same because the stoichiometry ratio of the reaction might not be 1:1, but it's supposed to be in the same order of magnitude. All right, so I convert the reactant to products. Concentration remains roughly in the same level. But if my product has very low solubility, like this picture, suppose the solubility of the product itself is really low, under the same temperature as the reactant. For the brief moment, this gap is supersaturation. And this is supersaturation of the product. And that is what we want. Okay? The question would be, how can we initiate reaction as we wish? How can we just click and let the reaction start? That can be controlled. That is sometimes very easy to achieve. For instance, we can put reactant in a vessel, in a beaker, and then initiate reaction by adding catalyst. The moment you add the catalyst into the beaker, that moment reaction starts. Before you adding the catalyst, nothing will start. That's the easiest way to control the reaction. Alright? For instance, if I have gold 3+, this is ion. If I do the reduction of the gold ions into gold 0, you can see that gold ion has very high solubility in water. For instance, you can add gold chloride into water. The concentration can be very high, at least in the unit of molar, maybe millimolar. But as soon as you reduce gold 3+ into gold 0 is solid gold. The solubility of solid gold in water is really low. Okay, so this is examples of this concept. In high school, we always put AQ here to represent gold ion in water. After reduction, gold 0 here is usually solid, right? But the question that I like to ask for you to think, should it be solid? Think about this. If I have 1 mole of Au3+, converted into Au0, solid gold particles, the status here is supposed to be solid. 1 mole of solid, right? But if I have 1 atom of gold 3+, 1 atom of gold 3+ in water should be indicated by AQ notation here. After the conversion, after the receiving of the electrons, gold 3+ will be converted into gold 0. Okay, 1 atom of gold 3+ should be converted into 1 atom of gold 0. My question to you is, 1 atom of gold 0, should it be represented by solid? 1 atom is not enough to form solid yet, right? So this state here is not quite a solid. The next question is, how many other atoms goes zero should have until it can be called solid. Just like in this picture, if I have one single atom of gold with the oxidation state of 0, it just simply gold atom, right? It is surrounded by water. It is not a solid gold yet, because solid gold is supposed to have solid structure. This one has no structure. Okay, so we cannot put solid notation here. So how many atoms are required for gold 0 to become solid? 2, 3, or the number of atoms required for one single lattice? That's not exact number that can be argued, right? The answer is that number of atoms supposed to be the same number as solubility. As long as I have the number of atoms equal to the solubility or exceed the solubility, then the solid will be formed, right? So at this state where gold 0 is no longer solid yet, the state here will be called as generic term as growth species. So please understand that the term growth species here is the transition state for what we want to form into a particles but not yet become a particles. Alright? So growth species supposed to have ability to move like atoms because it is not part of solid yet. So you have to imagine a growth species as a mobile species in liquid. Okay? If several growth species come together to form larger cluster, and the number of atoms within this cluster exceeds solubility, then this cluster would be called solid. And the smallest number of atoms in this cluster that require them to form into solid, at this particular moment, conversion from growth species into solid occurs. Okay? We just change the notation from growth species to solid. That moment when the solid is formed, this particular moment is called nucleation. We start to form solid. At that moment, nuclei is formed. This group of the cluster is called nuclei. Okay? So the whole process here is what we call nucleation. So you see, concentration of our growth species supposed to exceed solubility first before nucleation can take place. But we would like the concentration of growth species to exceed the solubility much higher so that we can get the state that we call supersaturation before nucleation can form. Okay? The state of supersaturation is not stable, so therefore it's supposed to have very high Gibbs free energy. According to thermodynamics, low Gibbs free energy means stable. Okay? Thermodynamics dictates that the stable state is supposed to have negative change in Gibbs free energy. So the lower the Gibbs free energy, the more stable the system. For the supersaturation state, it is not considered as stable state at all, right? So at this state, Gibbs free energy is supposed to be very high. Anything with high Gibbs free energy is not stable, so therefore, naturally, the system is supposed to adjust itself so that Gibbs free energy of the solution is supposed to be lower. How can the solution remove the energy, or how can the solution achieve the reduction in Gibbs free energy? The easiest way is to kick extra amount of solute out. Okay? Out of what? Out of the solution to form solid. Alright? So you have to imagine, suppose you have solution, a liquid solution. Inside the solution there's a lot of solute. That number of solute exceeds solubility, making the whole solution unstable. In order to make it stable, you have to remove that excess amount of solute out of the solution. So you basically remove solute out of the solution to form solid. Alright? That process of removing the solute out of the solution into the solid is nucleation, or precipitation in general. Okay? So, in other words, precipitation process is a natural process to reduce excess Gibbs free energy of the solution. So at the end, we will end up with solid particles. Alright? This reduction in Gibbs free energy can be calculated or can be represented by delta G. Alright? I use V here as a subscript. The V here stands for volume. Because the reduction of Gibbs free energy, this is calculated based on unit volume of the solid that is formed. Okay? It can be calculated according to this simple equation, where C here is the initial concentration of solute before precipitation, and C0 is the equilibrium concentration, or the solubility. You have to notice that C over C0, because we were in supersaturation state, so C here, initial concentration is supposed to be higher than equilibrium concentration. So the ratio C over C0 is greater than 1. That means logarithm here is supposed to be positive. And the negative sign here was put so that the delta G will be negative. Okay, we have reduction in Gibbs free energy. Delta G is supposed to be negative. Alright. If I put this delta G and multiply by the volume of the solid form, solid particles, assuming the particles to be spherical. So the volume of particles is 4 over 3 pi r cubed, multiplied by the energy per unit volume. That would be total energy for the nucleation process, or the total energy change, basically, for the precipitation process. And I like to call this one shortly as a volume term. Okay? Because it was calculated based on the volume of the particles formed. And keep in mind that this volume term is negative. Okay? This energy, this is supposed to have unit of energy, is negative in sign because of this negative here. Now, when we go back to this process, you start from solution, that means pure liquid, and you end up with solid suspended in liquid. So there are two phases in the system now. The process of precipitation, or the process of nucleation, introduces solid into liquid. Whenever we have two phases, always there are interfaces, right? Or you can also imagine that whenever we have solid, always the surface of the solid. And we learn in chapter 2 or in lecture 2 that surface of the solid has surface energy. And this surface energy is an extra energy that makes the solid unstable. Alright? So on one hand, you may say that precipitation of solid out of the solution reduces energy of the solution. But on the other hand, formation of solid itself introduces extra energy. Okay? So this extra energy increases the Gibbs-free energy of the solid. Of course, solid now is a part of the system. So increase in Gibbs-free energy of the solid also increases the Gibbs-free energy of the total system. That energy depends on surface energy. Okay? If I take this surface energy and multiply by surface area, remember that surface energy depends on the area. The surface energy has unit of energy per unit area. So if I want to calculate total energy, I have to multiply by surface area of the particles formed. Again, assume the particles to be spherical. The surface area of particle is 4 pi r squared. Multiply by surface energy or energy per unit area, you get total energy. This energy is called surface term because it depends on the surface of the particles. And it is positive sign because it is extra energy added to the surface. Alright, we will call this one surface term. Now, the surface term increases delta G, or increases the energy of the whole system. But the volume term decreases the energy of the whole system. So there are two contradicting functions. One function, the red function, tries to increase the energy of the whole system. The blue function tries to decrease the energy of whole systems. Okay? Both of them depends on size of the particles. So if I plot these two functions with respect to the radius of the particles, then I can get this picture. You should notice that the red line is a function of r squared. The blue line is a function of r cubed. Alright? If I try to find the net function, the green line here is basically the red line subtracted by the blue line. That represents total change in energy by this precipitation process. Alright? Mathematically, you just add these two terms together. Now, if I remove the red line and the blue line, consider the green line only, and you see that if I start from 0, r equal to 0, that means particle is very, very small, no particles yet, r equal to 0. The larger the particles, in some extent, okay, this area give the increase in total energy. And as you learn from thermodynamics, when you have delta G to be a positive sign, the system is not spontaneous. Alright? So this range, this area, is not spontaneous. What does it mean? It means that the particles formed with this size is not stable. If particles are not stable, then they will not be formed as a particle. They will dissolve back. Okay? It would rather stay in liquid rather than forming solid. In other words, in this range, surface energy is dominating. Right? On the other hand, if the particles formed by precipitation becomes larger than this value, then the energy of the whole system becomes negative. The process is spontaneous. In other words, if you can precipitate large particles, then that particles will be stable. Okay? The larger the particles, the more stable the system. Right? So according to the math, or according to thermodynamics understanding that we had, you can see that the bigger the particles, the more stable it is. But we want nanoparticles. We want small particles. Okay, so we want R to be as small as possible. According to this graph, what is the smallest radius that we can form to be stable? That would be this value, right? Smaller than this, the system is no longer stable. The particle dissolves back. Larger than that, although particles are stable, but we do not want large particles. Alright? And this graph, so that means when we start from no particles, or R equal to 0, and you have to imagine growth species swimming around in liquid. When growth species meet together to form cluster, and cluster size becomes larger and larger, you are going from this point toward the right hand side of the graph, become larger and larger until you get this point. Not until you get this point. That cluster is not stable. They dissociate back to growth species. Unless growth species comes together to get bigger cluster than this point, then nucleation takes place. Okay? So some people imagine this shape or this hump here as a barrier. You need to overcome this barrier before you can get stable size of the nuclei. So sometimes this location is called R star, or critical size. Okay? So some people consider this critical size according to the barrier location. But some other people use R star to be this size according to thermodynamics. That when you get critical size greater than this point, your particle is stable. So whether your critical size is here or there depends on your definition. Okay? But anyway, it's not significantly different. So, as I said, when the size of the cluster is smaller than the critical size, the cluster is not stable. The cluster dissociates back to growth species. If the cluster size is larger than the critical size, then the cluster becomes stable. It is called nucleation. Okay, the nuclei is formed. So you have to imagine the growth species swimming around. At one particular moment, 2 or 3 growth species collide together, forming a cluster. If that size is larger than critical size, then that would form a solid particles. Okay? Now, the green line was formed from 2 functions. The surface function represented by red line, and the volume function represented by blue line. Okay? If the level of supersaturation is increased, that means if I can create concentration of growth species within the liquid to be much higher than solubility of that growth species, so I increase supersaturation level. Okay? You should see that supersaturation level has nothing to do with surface energy. It has nothing to do with the red line, because supersaturation level is associated with concentration inside the solution before particles, the solid particles, are formed. But the red line is a function of energy that was increased because of the formation of solid. So whether or not we have high or low supersaturation level, it does not change the red function at all. Okay? But the blue function, this blue function depends on the reduction of energy. And that delta GV is a function of concentration over concentration zero, right? So the higher the supersaturation level, the higher that C over C0 ratio. So the blue function depends on supersaturation level. As we discussed, we can create supersaturation by decreased temperature or change the reactant to products. And the third one is using different solvent. All right. Now, the higher the supersaturation, the higher the delta GV. And when you multiply delta GV with R cubed, that function would reduce down more quickly. So this blue line would go to the left-hand side, like this, when you increase supersaturation level. The dotted line occurs when you have low level of supersaturation. The solid line here occurs when we have high level of supersaturation. The higher the supersaturation level, the more this function goes to the left-hand side. In other words, the function goes down as quickly as possible with respect to R, the size of R. So when you add this solid blue line to the red line, you see that the green line will be affected by supersaturation level. The higher the supersaturation level, the more green line shifted to the left-hand side. That means this peak would shift to the left-hand side. You should also see that when the green line shifts to the left-hand side, the critical size becomes smaller, right? Whether or not you consider this position to be critical size or this position to be critical size, it doesn't matter. When you have higher supersaturation level, the critical size becomes smaller. So that means if I want the smallest particles possible, I need the solution to achieve supersaturation as much as I can. So supersaturation is very important to get nanoparticles. Okay? Now, if I plot between concentration of the solution before nucleation, at this diagram shows you that the concentration of the solution is higher than equilibrium concentration or higher than solubility. That's why we call it supersaturation. Okay? So, as I said, we want supersaturation level to be higher. So we want to increase this level. Okay? We can do it by, let's say, produces more product if the growth species is formed by the reaction. Okay? If you increase the reaction rate to produce the products as much as we can, you can get high concentration of the product within brief period of time, and supersaturation level will be high, like this picture. Okay, so we have increase in supersaturation. So the higher the supersaturation level, the smaller the particles that you can get. How can we get this high supersaturation level? You increase the rate of reaction. Right? Or theoretically, you can also decrease equilibrium concentration, decrease solubility by decreasing the temperature. When you decrease the temperature, equilibrium concentration will be decreased down. At the same concentration in the solution, you can also achieve the supersaturation level as well. Alright? all of this should give you decrease in critical size, and you should see that this extra box, the red box here that I highlight here or there, means that I have much more extra solute that needs to be kicked out from the solution. So not only that supersaturation gives you small particles, it also gives you much more number of particles. Okay? The size will be smaller, the number will be larger, or more particles will be formed. So that means the higher the supersaturation level that you can achieve, you get a lot more small nuclei. If you get small level of supersaturation, you get a few large particles. Okay? Now, if I plot between solute concentration, let's say concentration of the growth species, with respect to time, okay? If I start the reaction to convert reactant into products into growth species, the concentration of growth species increases with respect to time. At time 0, that is the time when I initiate the reaction. Once the concentration of the growth species reaches the saturation level, this is called saturated solution. Okay? At this point, no nucleation will be formed yet, even though the concentration may exceed the saturation level, because at this point, the cluster size has not yet greater than or larger than the critical size yet. We have not overcome the energy barrier yet. Okay? So still we can produce more and more growth species by keep the reaction going. In that case, concentration of growth species exceeds saturation point. That's called supersaturation. Alright? So the higher the supersaturation level, there's more chance, or you produce a lot more growth species. So growth species is swimming around. There will be more chance for growth species to collide with each other to form cluster. Okay? The higher the concentration of the growth species, the higher chance for the cluster size to be larger than critical size. So the moment that we can get size equal to or larger than critical size, that moment you achieve critical energy. So you go over the hump in the green line graph I showed you earlier. Okay, so R equal to R star. So that point nucleation occurs. Of course, at one spot in your beaker or in your system, nucleation might form. Another location might not yet form the nucleation. So still, the concentration of growth species can go over that point. But from this point on, nucleation already takes place. So once nucleation takes place, concentration of growth species will start dropping. That concentration, I mean concentration in liquid phase. Okay? It starts dropping because extra amount of growth species form into solid, and solid is not counted in the concentration of the solution. But you should see that this point, concentration of growth species in the liquid still exceeds saturation. Okay? But it is less than critical now. So no more nucleation will be formed because it is lower than critical point. But concentration still exceeds the saturation. Still, the solution is not stable. Solution needs to kick solute out. But nucleation cannot be formed. How can we kick solute out? That extra solute would be attached to the existing nuclei, making the nuclei bigger while reducing the concentration of solute in the solution. So the concentration of solute in the solution goes down. Okay, this period no nucleation is formed, but the nuclei become larger and larger. This period is called growth. Okay, so the graph can be divided into three sections or three areas. In the yellow one, nothing happened in the solution. We just create supersaturation. In the red area, we get nucleation. Okay, nucleation takes place in the red area. And in the purple area, you get growth. Okay, so growth of the nuclei. Of course, one may argue that in the red area, we form nuclei everywhere in the beakers. Is there any chance that the growth species that is formed by reaction would attach itself to the existing nuclei in the red period? It can. Okay, so in the red area here, not only that we have nucleation, we will have nucleation and growth. But in the purple area, we will have growth only. Okay, the growth would go on and on until the concentration of growth species reaches saturation point. In that case, the solution becomes stable and growth would stop. So the question, what does the desired graph look like for nanoparticle synthesis? Think about this. We want particles to be small, and we want particles to be uniform. So we want the nucleation to occur almost at the same time. If I go back to this picture, we do not want this period to be long, because the longer this period, that means I have nuclei formed at different periods of time. The nuclei that is formed earlier would grow first. The nuclei that formed later would go next to it, right? So that would end up with particles with different size. The size will not be uniform if this area is large. So we want this area to be really, really small. But we want this level to be really high because we want the high supersaturation. Okay? The higher the supersaturation, the smaller the particle size. Remember? So we want this graph to be as sharp as possible and drop down as quickly as possible. We do not want this purple area at all. We do not want our nuclei to grow. But it is impossible to avoid growth. But we want the growth to be as small as possible. How can we achieve that? You have to think about that. Okay? The preference of the particles, basically we want all particles to be formed at the same time. The particles are formed from the growth of the nuclei. So we want nuclei to be formed at the same time. That's why we want nucleation period to be as short as possible, so that we get particle with uniform size. That can be done by increased concentration of the growth species abruptly. Okay? How can we increase the concentration of growth species abruptly? Basically, you need to initiate the reaction as fast as possible, right? So think about this. If you have gold chloride solution, okay, in a beaker, and we can reduce gold by using some kind of citric acid. If you slowly drop citric acid into the beaker, reaction will start but progresses very slowly. The concentration of gold zero formed by the reaction would be increases but slowly, right? But if you dump all the citric acid into the gold as quickly as possible, then the concentration of the product would be increased as quickly as possible as well. That's one way to do it. Okay? You can also increase the concentration of the products by controlling rate of reaction. How can we control the rate of reaction? Rate of reaction depends on concentration of reactant, depends on temperature. Usually, the higher the temperature, the higher the rate of reaction. So many reactions used for the synthesis of nanoparticles is usually performed at high temperature because we need high rate of reaction. Then we want to stop the reaction as quickly as possible. We do not want the reaction to go on and on and on, because continuous production of the growth species gives you growth. We do not want growth, right? So how can we quickly bring the reaction below critical concentration? That's normally it's done by controlling concentration of initial reactants. We want reactants to quickly react and then goes out. Okay? For the growth process, there's 4 steps. First is a generation of growth species. It's usually done by reaction. Okay? So suppose I have nuclei formed in liquid, growth species formed by reaction. Okay, let's say I reduce gold ion into gold 0. That one single atom of gold 0 is called growth species. It's formed in liquid somewhere. This growth species, as I said, has ability to move just like atom. Movement of growth species can be done by diffusion. Okay? So, if you consider concentration of growth species around here, is supposed to be higher than concentration of growth species on the surface of the nuclei. Why did I say that? Because whenever we have growth species on the surface of nuclei, growth species would become part of the solid, and the concentration of growth species in liquid around that area would become 0. Okay? So now when we have high concentration of growth species in liquid here and low concentration of growth species in liquid near the surface, that creates concentration difference. That concentration difference is a driving force for diffusion. So growth species would tend to diffuse. And according to transport phenomena, we can represent diffusion by a process of movement through what we call mass transfer foam. Right? So there be diffusion through the foam. Once the growth species diffuses through the foam onto the surface, the landing of the growth species on the surface is consisted of 2 steps. First one is basically adsorption. It absorbs on the surface. It's not part of the surface yet. Okay? It just lands on the surface. It can still walk around on the surface. Walking of this growth species like so is called surface diffusion. Okay? Once the growth species finds a good spot on the surface, it will be bound to the surface as part of the solid. This binding occurs, of a bond would be formed. This is the 4th step, called incorporation of growth species onto the surface. Once it's incorporated into the surface, it will be a part of the solid. And then this is the process called growth. Alright? So the growth can be divided into 2 groups, blue one and the red ones. The blue ones depends on growth species in solution, and the red one depends on the solid. Okay? The blue one, since it depends on whatever inside the liquid, sometimes whether or not the rate of these 2 steps will be fast or slow usually depends on diffusion of growth species in liquid. On the other hand, the red ones here depends on how fast this growth species attach itself to the surface. This one is what we call whether it's fast or slow depends on surface process. Okay, so if I have 4 steps, the slowest steps would be rate determining steps. So in growth we can have diffusion control growth or surface control growth, depend on which steps, blue or red one would be the slowest. Okay, we can derive mathematically to find that if diffusion or the blue steps control the growth, if the diffusion is the slowest step, then the longer the growth time means the decrease in radius difference. What does it mean, decrease in radius difference? This means if we have 2 particles with different size, okay, the longer the growth period, 2 different particles would become almost the same size. Okay, decrease in radius difference means 2 particles becomes almost the same size, which is good, which is what we want. So eventually it brings into uniform size distribution. On the other hand, if the surface process control the growth, if the red steps in the growth steps is the slowest, then it can be divided into 2 categories. First one is called mononuclear growth. Mononuclear means the growth species must land on the surface layer by layer. Okay, the first layer must be completed before the second layer will be formed. In this case, the longer the growth time, the more difference in the size, which is not what we want. Okay. On the other hand, if we have polynuclear growth, which means the first layer does not have to be complete, the second layer can start right away, then it should give you constant growth rate, which favor the mono size. The question that you might ask is, how can we control to be mononuclear or polynuclear? Actually, you cannot. Okay, whether it is mononuclear or polynuclear is basically a manner of mathematical derivation. So since we cannot control it to be polynuclear, okay, it would be better to control it to be diffusion control, right? Think about this. We have growth steps to be either diffusion control or surface control. If it is surface control, it depends whether it's actually mononuclear or polynuclear. All of them we cannot control. So, in order to get particles with uniform size, and we can control it, we would prefer the growth process to be diffusion control. Okay? So how can we control the growth process to be diffusion control or diffusion limit? Basically, we want diffusion to be rather slow. Okay? How can we make diffusion to be slow? The growth species is supposed to be provided slowly by keep the concentration of growth species to be very low. Okay? If the concentration of growth species to be low and concentration of growth species on the surface will be low as well, diffusion will be rather slow because the concentration gradient is small. But wait a minute. Before we discuss about growth, we said that we want concentration of the growth species to be high to get supersaturation, right? Remember? But now for the growth, we want growth species concentration to be low. So which one is it? Do we want low or high concentration? Actually, you need to understand. First, nucleation takes place before growth. During nucleation, we want concentration of growth species to be high. For the growth period, we want concentration to be low. So that's why we want concentration of growth species to be abruptly changed from high to low. That means we want growth species to be consumed almost instantaneously. Okay. We can also control diffusion by controlling viscosity of solution. The higher the viscosity, the higher the slower the diffusion. Okay. Or we can somehow create diffusion barrier on the surface of the nuclei. What is diffusion barrier? If you remember on lecture 3, we talked about creating a bumper by using polymer layer on the particles, right? That polymer layer is considered as diffusion barrier as well, because the growth species must go through that layer before reaching the surface. We can control supply of growth species by control chemical reaction rate, either by control the concentration of reactant or the catalyst itself. Okay. As I said, don't be confused. The concentration that we need in growth steps to be low is different occasion to the concentration of growth species needed for supersaturation creation. Alright, so for this lecture, I just want you to understand the process of nucleation and growth. Of course, before nucleation, we need supersaturation. So these 3 steps, creating supersaturation, nucleation, and growth, are what the precipitations require. Alright? So we want precipitation to produce the nanoparticles. And precipitation requires supersaturation, requires nucleation, and growth. Okay? These are fundamentals of thermodynamics approach. Next lecture, I will give you examples and discuss all of these concepts with that examples. So see you on the next lecture.